So good evening, everyone. Welcome to this weekly interactive sessions of the NPTEL Gate platform. I'm Naresh, a research scholar in the Department of Civil Engineering at IISc. Today we look at the topic of connections in structural steel construction. So, so we'll look at the types of connections in structural steel. For example, we have welded connections, bolted connections, and riveted. And among welded connections, we have fillet and butt welds. And in bolted, we have uh, So bolted connections can be classified in different manners. One based on the type of bolt we use, whether it is a bearing type bolt or a friction grip type bolt. We can also classify them as either in plane or out of plane connections. So among in plane, again, bolted connections can be further classified into concentric and eccentric. So we look at all of these today, and we'll also look at a couple of previous year gate problems. So let us get started. So why do we need connections in a steel structure? So because standard sections, rolled sections, they come in certain shapes and sizes. So the length of a beam is not indefinite. We have standard sections that come are of several meters long. Similarly, you may have to connect beams to columns which are in two different directions. So these connections have to be typically assembled on the site. So, so the reason we have connections is one, because standard members have specified shape and size. So you may have to connect, for example, you can have a column, which is a I section, and you may want to connect it with a beam. So to do this kind of a connection, suppose this connection is, if you want to design it as a simply supported connection, which doesn't resist any moment, if you want to design it as a pin jointed connection, then you provide an angle cleat here, with an angle here, and bolt it. So in the design of connections, we see how do we design these bolts that are actually transferring the load from the beam. So beam may be subjected to some loads. These loads have to be transferred safely to the column. So these bolts are subjected to certain kinds of forces, and in the design of connections in structural steel, this is what we look at. How do we transfer uh, how do we design these components, the connections, and the components of the connection, such as the bolt and the welds. So we know that a structure is only as strong as its weakest connection. But connections are typically designed to be stronger than the members that are connected to the connection. So the connections or connectors are stronger than the members. So we typically keep the beam weaker than the connection was connected. Why is that so? Because the failure of because the connection is very small in size. So a beam, the typical length of beam is about of the order of 1 to 5 meters or even greater. It's at least a meter, but the connection spans a few mm. So it is of the order of say 300 to less than 300 mm. So when this undergoes yielding and the beam or the structural members connected to a connection undergo yielding, they deflect very large. So they small strain. So if you impose a strain of 10%, this undergoes a displacement of 100 to 500 mm, whereas the connection displaces only by a small quantity. Therefore, the ductility of a connection is much less than the members. The reason is ductility of the connection or the connectors is much less than members. That is why we don't allow the connections to yield. We always design the connections assuming that they behave in a linear elastic manner up to the point of failure. So we So the assumption in designing connections is that the connectors remain linear elastic until failure. But that is not the case with the members that are connected as well. So you know that if you have a tension member, we haven't done it before, but in the limit state design, we assume that the structure is at the verge of collapse, but that is, and we design it for the ultimate state. We design the members for safety at the ultimate state and serviceability at working for the service loads. But the connections, we always design them for we don't do a plastic design. We do a linear elastic design. We assume they are linear elastic until failure. Further,
Sir, can
then
you open the chat option?
yes.
Can you open the chat option? Can you enable it?
So that's the question, sir. Are you sharing the screen? I'm unable to know. That is not clear.
I think chat itself is disabled.
Okay, let me check settings. Hello, mic, hello, camera. But I don't see the option for chat. You're able to access the Q&A?
Yes, definitely.
So your screen is visible.
Okay. And yeah, this is on some other some other day. So.
Yeah, it is. These are different days. Yeah. We
Okay.
can continue with this.
Okay. Yes. So.
By the way, I have a question, sir.
Yes.
The ultimate failure is due to the component members or the connectors? Like which fails ultimately?
That depends on how we design it, and the desirable failure is it is desirable to
how we what is our intention of whether we are keeping the intention of failure of the component or the connector.
Our intention is always to have the failure in the component, not in the connector, because as you said, the failure of the members is much more ductile than the failure of the component. So that is what I said. If you take this typically of the order of 10 meters, so beam is 10 meters, say 3 meters long. And the connector is say 300 mm. So if this starts yielding and develops a strain of 10%, steel has a ductility of about 5%. So 15%. So if it yields to a strain of 10%, you can see a deflection of 1 feet, 300 mm. But here it is much smaller. The bolt yields, it's not going to show up easily. So there are less warning signs before a connection fails as compared to as compared to when the beam itself fails. So our intention is always to have the failure in the connected members, not in the connections. So the connections are always designed to be much stronger and rigid than the structural members themselves, because that also affects how we analyze the structure. We take a portal frame and we do a limit analysis of it. We assume that this so if you do a linear elastic analysis, we assume that this remains at 90 degrees. And if we idealize it as a simply supported, we assume that is perfect shear transfer. We don't allow for any slip here. So the connections are crucial both in analysis and from a failure point of view. So they are always designed to be stronger than the members. So shall I proceed?
Yes, sure.
Yes. Okay, so basically this is the assumption. We assume that the connector remains linear elastic until failure, and we do our analysis. So first we analyze the structure for the member forces, and then we apply the member forces that we have obtained onto the connector, and we analyze the connection, analyze and design the connections. And after designing the connection, we should check that whatever assumptions we made are actually satisfied. So if you assume that the connectors remain linear elastic until failure, after getting all the member forces and applying it on it and designing it, once we get the actual numbers, actual bolt diameter and things like that, we need to check if the bolts really remain linear elastic until failure. That is the idea. So then what else? Yeah, so that is the key idea. So both from a safety and an economy point of view, we don't want the failure to happen in a connection. Then the common types of connections as we know. So we can have welded connections. We can have bolted connections. So again, among welded connections, we can split them. The two key types of welds are, one is the fillet weld. The other is a groove weld or a butt weld. There are other types of welds. So there are something called plug or slot weld, but those are not used. So in constructions, 80% of the welds are fillet welds and about 50% are butt welds or groove welds. These are not very common. So fillet weld is made by, suppose you have a plate and you have another plate, and we wish to connect these two. So fillet weld is made along the corner between the two. So there are no direct stresses acting on a fillet weld. Typically, a fillet weld is made such that the stresses that come onto the weld are predominantly shear. So if this plate is subjected to some force P and we want to connect these two plates, this is how we make a fillet weld. On the other hand, if you wanted to connect two plates with a groove weld or a butt weld, we place them such that their edges face each other. Their edges are chamfered for providing a full penetration butt weld, so that we can place the electrode without much. While making the arc weld, we can place the electrode without any discomfort, resistance. So, and this portion is welded from both sides. So in this case, you can see that the weld is subjected to direct tension. So this is what we call as a groove or a butt weld, and this is a fillet weld. So this we can also have partial penetration tools. You can have something like this, where we don't cut until the end, and only a part of it is filled with a butt weld. These are not very useful. They are used in they are not advisable under fatigue loading and when we have load reversals. So this, when it is when the weld is predominantly subjected to tension, it is butt weld, and when it is placed such a way that the resistance comes from the shear at the interface between the parent metal and the weld, it is a fillet weld. So there are various configurations of the joints that you might be well aware of. You have butt joint, where this is a kind of a butt joint. This is a lap joint. Yeah, and there are several, and you can have some T joints and corner joints. So, but what are more important in steel structures are, one is a lap joint and butt joint. So T joints occur when you want to connect something to a column. You want to connect a beam to a column, get a T joint. So this may be the face of a column. And the beam is connected to it by a. So this is a T joint. What we have here is a T joint, if it is welded. So in a welded connection, first, if we look at welded connections, so benefits are that they are lightweight. So you don't have extra components, so they're very lightweight. They have good aesthetics. You don't have holes in it. They don't damage the material, so they are lightweight. So lightweight, no holes. So they're aesthetically appealing. And also holes are the points of stress concentrations. So when you don't have holes and when the material is truly continuous, it is always preferable. They don't have any holes. They cause less damage to the material. They're also fairly rigid. But the disadvantage is that they are not suitable for fatigue load. So disadvantage is that they are prone to fatigue cracking because it is an interface between two dissimilar materials and it holds only by atomic bonds. So a weld is basically formed. It is just heated up and it forms the atoms form new bonds and the material fuses together. So it's always an interface between two different materials, which is at a higher energy and it is not favorable. So always fatigue cracking and cracks develop. It is very prone to cracking. So it is not advisable when we have cyclic reversible loads. That is why all the railway bridges in India, or not just in India, railway bridges always have bolted or riveted connections because they are subjected to cyclic loading, which subjects the wells to fatigue loading, and it cracks under fatigue loading. So fatigue cracking is a big disadvantage of welded connections. Also, it requires skilled manpower at the time of construction and other practical difficulties. So how do we analyze welded connections? So analysis of fillet wells. So to analyze fillet wells, we consider what is called the throat of the weld. So suppose this is a plate. And it is lap jointed to another plate like this. So this is how the fillet well connects the two. It may be subjected to some forces speed. It's also a fillet weld here. So the first step, as always, find out the, so this is a connection between two members. So find out what are the forces coming onto this moment. So treat the weld separately. So weld can be of any shape. Weld is usually something like this. You can't get a perfect triangle. But the effective region that is resisting the applied forces is taken to be the largest triangle inscribed in the weld. So in realistic applications, the weld will have some complex shape. But what is useful is the largest triangle inscribed in the weld. So take the largest triangle inscribed in the weld. It may have, so call the smaller one of the two right angles. So take the smaller one of the two right angles as S. There can be all kinds of forces acting onto this weld. It can be a force, it can be an axial force, there can be a shear force, and so on. But as I said, a fillet weld is weak in shear. So the place where it is bonded to the parent material has high shear stresses. There are forces coming onto this. So if this the plate is subjected to a force P and it is connected to this plate by another weld, so this is subjected to a force P. So equal and opposite forces. On the plate, it will be like this, and on the weld, it will be in the other direction. So there can be forces coming onto the weld in this direction. There can be shear forces coming onto the weld in this direction. So let us call them some Fx, Fy. There can also be other axial forces which act out. So the base of the weld where these two lines meet is called the root of the weld. And the minimum cross-sectional area is where failure is susceptible. So this is the hypotenuse. So that is very large, and that's an external surface. So it's not going to fail there. It can fail here, or it can also fail somewhere in the middle. And if this is a right triangle, if it is an isosceles right triangle, then you can take this line bisecting the right angle is the smallest cross section in the weld. So this smallest cross section in the weld is known as the throat of the weld. And this length is called the throat thickness TT, the nominal or the effective throat thickness TT. So TT is the throat thickness. And that is, we assume that all the forces is resisted by this. So this is a plane. So the weld extends into the plane of the paper. So you have a plane like this, over which all the forces applied on the weld can be resolved. So you can have, so the weld is likely to fail along this plane. So So given a welded, given some configuration and the connection and the weld, or how do we design the weld? So we have the partial safety factors. So gamma MW. So this is the material partial safety factor for the weld. Is taken as 1.25 if the weld is made in shop and 1.50 if it is a field weld, because it is more likely to have imperfections when the welding is done on field. So this has got a higher partial safety factor. The strength of the weld is given as, so weld is likely to fail in shear if FUB is the ultimate tensile, FUW is the ultimate, so if FU is the ultimate tensile strength of either the weld material or the parent material. Typically, the weld material is much stronger than the parent material. So FU is always taken, FU is the lower one of the two because it's an interface. The low, whichever is the weaker, that one will fail. And typically the weld is stronger. So the strength of the parent material will govern the design. So we have FU, which is the ultimate tensile strength of the parent material. But we know that the weld is going to fail in shear, not in tension. So can replace it by FU by square root of 3. FU by square root of 3 is the ultimate shear strength of the weld. And we do a limit state design, so you can apply this gamma MW. This value should be greater than or equal to the shear forces acting onto it. So this is the factor shear stress coming onto the weld. This should be greater than that. This is the ultimate this is the ultimate shear strength of the weld divided by the material partial safety factor. This is the factor shear stress coming onto the weld. And what is Q? Q itself is given as the factored shear force. Let us say the factored shear force is Fs divided by the throat thickness times the length of the weld Lw. So that is it. So this is the factored shear force by this. Not only that, but this is under pure shear case. This is under the case of pure shear. But you can also have tension coming onto the weld. So the entire weld can be subjected to tension in this direction. So this is not acting at the interface. This is some tension like this. You can have tension acting along the weld. So let that tensile stress be Fa. Again, Fa, this tensile stress acting on the weld is also given as Fs by the corresponding area. So you can have whatever area is resisting the tension. So you can have tension either in this, either along the length of the weld, or you can have it along the along this direction. So under a combined state of loading, we have Fa based on the von Mises yield criteria. We know Fa plus 3 times Q square. So Fa square plus 3 times Q square. If you remember, the von Mises yield criteria from the strength of materials is given as the the sigma xx square minus sigma xx minus sigma yy the whole square plus sigma yy minus sigma zz the whole square plus sigma zz minus sigma xx the whole square plus 6 times sigma xy square plus sigma yx yz square plus sigma xz square. So this entire thing divided by 6. So the von Mises yield criteria says this should be equal to the, so this we call as the von Mises equivalent stress divided by 2. So let us call it, when this reaches the yield stress under uniaxial tension, that we take as failure. So if you substitute everything in this case, the axial force comes out to be, that will be one component of this. So that will be a 2 times Fe square. And the shear stresses together will be 6 times the resolved shear stress onto that plane. So the net should be equal to sigma this, which is the failure stress of the weld itself. So we have a square on both sides, so take a square root. This 2 gets cancelled with the 6 and the 2 times sigma xx squared, which is 2Fa squared. So this should be less than or equal to Fu by, you don't have a root 3 because that von Mises stress actually relates it to the uniaxial tension experiment. So you have plus by gamma m double. So under a combined state of loading, the axial stress coming onto the weld plus 3 times the net shear stress coming onto the weld, the whole square, should be less than or equal to the ultimate strength of the either the weld material or the parent material divided by the material partial symptom. And for and how do we determine the throat thickness? That is, so for this is S and S for an isosceles right triangle. This is the throat thickness TT, and we know it is given by S by root 2 or 0.707 S. So that's all it is. Then so for everything other than this, it is problem specific. So a fillet weld can be loaded along the, it can be a side weld or an end weld. You can have, if you have 2 plates, you can have a fillet weld along the sides, or we can also have it at the end. So that is taken care appropriately. Then and then we can look at butt welds. So we'll look at a problem very soon. So butt welds or groove welds. So if we, so as I say, they are preferred when we want to connect 2 plates facing each other, whose edges are facing each other, in order to ensure that the faces are fully bonded, we typically provide a chamfer, and the region in between is filled with a weld material. In this case, we call it a full penetration groove weld, and the thickness of the throat in this case is not any. So the effective throat thickness, which is resisting the applied tension, is this. So the throat thickness is the entire depth of the plate. So if you have a butt weld, the throat thickness is the thickness of the plate or the thickness of the thinner one. So thinner plate. So if you have 2 plates of different thicknesses connected to each other, then we should take the thickness of the thinner plate. So what else? Yeah, that's almost. So while dealing with lap joints and butt joints, these are the types of welds we can have. When dealing with brackets, when we, so we can also have welds placed in eccentric connections. So these are all concentric connections where the forces are acting along the same line. Eccentric connections are common in beam column joints. So you can have a face. So this can be the flange of a column facing us, and it can be a beam which is placed in this fashion. So there need to be some support here. So if this is a bracket that connects a beam to a column, the bracket is subjected to some concentrated force coming from the beam. The bracket can be welded to the flange of the column. In this case, the force doesn't pass through the weld itself. It is eccentric. So if you consider the equivalent system of forces coming onto the weld group, we have forces and in-plane moments. How do we analyze this? As always, we assume that the members, we know the forces coming from the members based on some preliminary analysis. We assume that the weld group behaves linearly elastic. And we assume that, so this is an in-plane, there's an in-plane moment coming onto the weld group, and there's also a in-plane shear force coming onto the weld. So as we can see above the center of the weld group, this moment tries to twist it. So we assume that it's not strictly speaking, this assumption is not valid at all. So we assume that because it is not a it's not the torsion of circular shafts, but we assume that this moment is resisted by the weld group such that the stress in the weld is proportional to the distance from the center of the weld group. So if this total moment is T, the twisting moment, the total in-plane moment is T, and the total in-plane shear is V. We assume that the entire area of the weld group is equally stressed under the shear force. So shear forces on the weld group are uniformly distributed. So this is one assumption. That is not, strictly speaking, that is not true, but we don't have any other option. And the twisting moment follows the obeys the usual assumption under twisting. What is it? So the twisting moment into the radial distance from the center divided by the polar moment of inertia is equal to the stress. So the stress in the member at a point, so stress at any point, if the radial distance from the center of the weld group is S, the stress at this point in the weld group is given by the total twisting moment T into S divided by G. So this is a simplified analysis for in-plane eccentric loading. We can also have out-of-plane eccentric loading, which is the case with beam columns. So let me draw. Suppose this is a column. And this can be a beam which is welded to the column itself. In order to, we can have a weld both at the flanges and the web of the beam. So this beam can be subjected to some forces, and that will, if you take a view this way, the weld group will appear something like this. And there are both bending forces and shear forces coming onto the weld. So the weld group is subjected to a certain shear force V, and it is also subjected to the bending moment. So this is an out-of-plane eccentric connection. In order to design the out-of-plane eccentric connection, you assume that the bending formula or the assumption of plane sections remaining plane and all that, and the linear distribution of stresses holds. So we assume that the distribution of stresses in the weld group is linear. So what does that mean? Which means the bending formula as well. So the shear forces, again, we take the shear stress in the weld group as simply V by A, where A is what? A is, if it is a fillet weld, it is nothing but the throat thickness into the length of the weld, the total length of the weld. And the bending stresses, sigma xx, are given as the bending moment M into the distance from the neutral axis Y divided by the moment of inertia about the axis of bending. So bending is about the Z axis. To take the moment of inertia about Z axis. In addition, you can also have tensile forces acting on the weld. and those are also assumed to be, although it is a tensile force on the weld, it will be resisted by shear weld. So that component of sigma x is coming from tension is nothing but, if the tension is say P, it's just P by A. And these are combined in a suitable manner, and we use the same formula, square root of Fa square plus 3q square is less than or equal to Fu by gamma. So this is all about welded connections. If you have any doubts, I can answer, or before I go to bolted connections. Are there any doubts? Let me check the Q&A in case you have. Okay, fine. There are no doubts. Okay, assuming there are no doubts, let me go to the bolted connections part. So coming to bolted connections, they are very easy to fabricate in the field. So they don't have to be manufactured in a shop, and they're very easy to fabricate in a field, in the field. So what else? So that is one benefit, and they're also suitable for fatigue loading. So the benefits are can do. They can be made in the field. They can be assembled in the field, and they are, as I said, they are suitable for fatigue loading. They don't crack away. They don't cause. They don't cause cracks. They don't cause crack growth, fatigue crack growth. So they are suitable for this. But as I said, the disadvantages, it is puncturing the members themselves. Disadvantages is they reduce the section of the members. There are holes, so they reduce the section of the members, and they are not continuous. So there is a discontinuity. But the bigger problem with one type of bolts called the bearing thread bolts is that there is always a slip. It is not, since it is not continuous, there is always some slip before a bolt comes into action, and it takes up the load. If you have suppose we have two members which are connected by a butt joint. So these two members are facing each other, so it is a butt joint. And we have two cover plates on top and bottom, one on top and one on bottom. So this is called a double cover butt joint. So this is what we call double cover butt joint, and the bolts are placed in this direction. So just have this example in mind. We'll see how to. So again, bolted connections. So this is an example of concentric connection. Why? Because the forces are concentric. They act along the same line. So this is a concentric bolted connections. We can also have eccentric bolted connections, as in the case of welds. So where do eccentric bolted connections occur? Similar application. You can have a bracket supporting some load from the beam. So bracket is bolted to the face or flange of the column instead of being welded. So this is an eccentric in-plane bolted connection. So this is an eccentric in-plane bolted connection. We can also have eccentric out-of-plane bolted connections, which are also known as moment resisting joints. So it can be in plane or out of plane. For out of plane, you have the same example. This is the face of the column. Instead of there, we welded just a beam directly, but in this case, you can have a base plate. Or rather, if it is a simply supported beam, you provide two angles like this, place the web of the beam, and connect them with bolts on both sides. You can have you can bolt the angle to the flange of the column, and you can bolt the angle to the web of the beam as well. So in this case, this bolts, if you see, they are subjected to out of plane forces. There is the beam can be subjected to some loading. That will be transmitted to the column as a combination of in-plane shear and out-of-plane moments. As a result, if you take the section of the column, so the column looks like this. There's an angle which is connecting to the beam, and there are also bolts. So these bolts are subjected to compression and tension. These forces are out of the plane of the bolt arrangement, so these are subjected to out of plane load, eccentric out of plane load. So the next so that is at almost all of it. The next classification of bolt comes from the type of bolted connection. So the type of forces, what is the mechanism by which failure of bolts? So I told, remember this example, right? So take this example. If you draw the free body diagram of the bolts in action, how does it look like? If you take the plate itself, if you take the top plate, you have a slot here into which the bolt is inserted. So the bolt is something like this. Let me draw an exaggerated view. We have the top plate here subjected to some force P. Because of equilibrium, there will be an equal and opposite force exerted by the bolt on the slot of the plate. So on this face of the, so this is a hole in the plate. On this face of the hole, you have some distribution of forces whose net force is equal to P. Again, by equilibrium, this force should be equal and opposite or to the force on the bolt itself. So the bolt is subjected to a force. It can be some distribution, but the total is P. So yeah, I'm sorry. So there is a cover plate on top. So this P is actually applied down. So this is the middle plate. So this acts here. The total force is P, and there is some distribution of pressure onto the motor. Next, consider the top plate. The top plate also has got a slot. The bottom is being pulled this way. The top will be pulled in the opposite direction. So on this slot, this is subjected to a force of P by 2. The top and bottom, these two plates share half of the forces. So the top will be subjected to a force of P by 2. The bottom will also be subject to a force of P by 2. Therefore, equal and opposite force will be exerted by the bolt onto the plate on the opposing bearing surface. So the force on the bolt will be P by 2 here and P by 2 here. Now, what does this do to the bolt? So this system of forces, you have one force like this, you have one force like this, and one force like this. This can shear the bolt at these locations. So if we take this cross section, the section above that is subjected to a right side force, and the section below that is subjected to a force towards the left. So there is a shear coming onto this cross section. So the bolt can go into 3 pieces like this. And if it is ductile enough, this is what will happen. It will yield in shear, or it can break in shear. So this is shear failure of the bolt. Alternatively, this force comes as a concentrated force onto a very small cross-section area of the bolt itself. So initially, if the bolt cross-section viewed from the top is something like this, because of the action of this concentrated force coming from the bearing of the plate onto the bolt, this portion can, so this is also a concentrated force. The stresses are very high near the application of this point of the force. So the bolt, it can either yield or it can break under the action of this high stresses. So this region is highly stressed. So this can either yield or break and fail, the connection can fail. So that is called a bearing failure. And if you look at out of plane connections, out of plane eccentric connections that we saw, can have a, so it is the top bolt is subjected to some tension. So this, in this case, the bolt, a region here, it can just yield and then neck and then undergo tensile failure. So you can have tension failure. But what is the assumption here? It assumes that when we apply the force, this surface, the surface of the slot comes in contact with the surface of the bolt, and the forces are transmitted by contact. So when there is an actual contact of the plate and the bolt itself, we call them bearing type bolts. So until bearing happens, there is no contact between the bolt and the surface of the slot itself. So there is no force transmitted. So when we increase the force from 0 to whatever service load is going to be applied on the connection, initially there is no resistance at all. It just slips. There is a displacement due to the slip of the plate with respect to the bolt. Once it comes in contact, then there is a steep increase due to the connection. So these type of connections where there is an initial slip is called bearing type bolts or slip non-critical bolts. So slip is not critical in this kind of connections. We can also have high strength friction group connections where you have two plates. Let us just consider two plates for simplicity, and they are to be connected by a bolt. So in high strength friction grip bolts, the bolt is tightened to more than, so this is the bolt, and it extends on both sides beyond the shank. So sorry, the shank extends on both sides beyond. So this is the nut. So if you tighten it beyond whatever is required, so bearing type bolts are just snug fitted. If you tighten these extra, what happens is the bolt is subjected to a tension. So now if you draw the free body diagram, the bolt is subjected to tension. What happens as a result is that equal and opposite compression develops on the plates. So you tighten it and then you leave it. This is not an externally applied tension, right? So you tighten the nut more than what is required. So it will move closer and closer to the, so these nuts will, if you tighten it more than what is required, they tend to move closer, but there is the surface of the plate resisting it. So if you draw the free body diagram, this shaft of the bolt is subjected to some tension, and there are no external forces acting on it, so it has to be self-equilibrated. So the plates will press against each other with some compressive force. So we have removed the bolt. This is the slot. The plates are pressing against each other with some compressive force. And if you draw the free body diagram of one plate, there is some compressive forces here over the interface. What will that cause? So that will press them against each other, and these surfaces are not ideal, they are not smooth. So when it is not loaded, we just have a compressive force. When we apply a certain force, if you remember, there is always friction. So if you assume a Coulomb friction model, the friction developed, there is a friction developed which is equal. So if you integrate all the frictional stresses, you can call them stresses acting on this surface, that should be equal to the applied force P. If there is no slip, and if there is slip, it is equal to some limiting value of friction, which is given by some mu times the normal force on the bolt. So the normal force coming, what is the normal force? Normal force is given by the tension in the bolt divided by the area of the interface. So that's all it is. So this connection will begin to slip. So this is called friction grip. Because of excessive tension in the bolt, the plates are compressed against each other. And as a result, when we apply some force, the predominant mechanism by which the applied load is resisted is by the friction between the two plates. Not the bolt is not bearing against each other. So if you draw the free body diagram of bolt, there are no lateral stresses. There are no lateral forces acting here. Entirely the applied force is carried by the friction between the plates. So these are called friction grip bolts. And these are they're expensive, but they're very efficient. They are used both in the case of, they don't allow for any slip. So that issue is not there as with bearing type bolts. And they can also be adapted in, they're very good for fatigue loading where you have cyclic reversal. So the capacities, these are given by the IS 800 2007 book for, if you take chapter 10 of IS 800, you can find these. The capacity of the bolt to resist the design shear capacity of a bearing type bolt is given by this, where A and B is the net area of the bolt. So if you take a bolt, there is the shank area, which is smooth, and you have the threaded area, which is the net area. So typically this area is smaller than the area of the shank. It's about the factor of 0.8 or so. So this is the net area of the bolt. So this is net area A and B. This is the shank area ASB. N is the number of shear planes. So in this case, in the example that we have considered here, there are two places. So there are two sections in the bolt that are resisting the applied force. So here N, one of them may pass through the shank area, one of them may pass through the net area. So the number of shear planes passing through the shank area is Ns, and the number of shear planes passing through the net area is Nf. So this is the ultimate shear strength of the material of the bolt, and this is the partial safety factor. Similarly, so gamma MB is always 1.2. And what is the bearing capacity? It is given by a similar formula. This is partly empirical, 2.5. Kb is some factor. dt is the nominal bearing area of the bolt. So d is the depth, the diameter of the hole. T is the thickness of the smaller plate which is connected. And it's either the diameter of the hole or the bolt itself. So the smaller one is typically the bolt. Fu is the ultimate tensile strength of the plate connected, not the bolt. It is the ultimate tensile strength of steel. And gamma MB is the partial safety. This KB is given by the minimum of edge distance by 3D naught. So what is the edge distance? So edge distance is this. Distance from the edge of the plate to the first bolt. Pitch is this. 50 mm is the pitch in this case. The distance between two subsequent arrays of bolt is P. And FUB by AP. So the smallest one of these factors have to be considered. And the tensile capacity is given by this 0.9. FUB is FUB AN by gamma MB. So if you don't have this, you can understand. So FUB AN by gamma MB is the force, ultimate force. This factor of 0.9 is given to account for ductility. But note that this has to be less than or equal to FU, not FUB, this is FYB. Fy, the yield stress of the bolt, into ASB divided by gamma M0. So this is Fy. This is the ultimate, this is yield stress multiplied by shank area of the bolt divided by gamma M0. Why is that? So gamma M0 is 1.1. Because we don't want the bolt to yield under service loads. So the design capacity should not only be less than, should not only be this 0.9 FUB AN by gamma MB, which is the net, the load at which the net area breaks under tension. This, not only this, but this has to be less than or equal. So you take this, in case this value is greater than the value given by yielding of the bolt. So FYB is the yield stress of the bolt multiplied by the shank area divided by the gamma M0. If this value is greater than this, you need to take this because you don't allow the bolt to yield under tension because it is not ductile. It is not as ductile as the molds. So in the case of friction grip bolting, we just have, as I say, NE is the number of interfaces resisting friction. And this is the bolt force. This is the force in the bolt. A and B into FUB into 0.7 is this is the proof tension force in the bolt. KH is some factor depending on the hole size. So if you have the clearance hole, it is 1. If you have oversized, it is 0.87. If you have a slot in which the bolt is inserted, then you have it is 0.7. Gamma MF is a material partial safety factor for the friction grip type. So this is given by a table in IS 800. So these are the capacities. We are already past time. Let us quickly look at some problems. So this is an old problem. This is in GATE 2010. A double cover butt riveted joint is used to connect two flat plates of 200 mm width and 14 mm thickness as shown. There are 12 power-driven rivets. So this is a riveted connection. Rivet is very similar to a bolt. Only thing is you don't have a net area and shank area. Rivet is the size of a rivet before it is inserted into its hole is larger than the size of the hole. So after it, so it is heated, then inserted. So once it cools, it regains its original shape. And because of that, it fits the hole completely. It doesn't. There is no slip. There's no slip as in the case of a bearing type connection. I have two cover plates of 10 mm thickness, and yeah, the plate is 14 mm. The cover plates are 10 mm thickness. What is the capacity of the joint in tension considering bearing and shear only, with permissible bearing and shear stresses? So this is an old. So this is as per IS 800 1984. Where the design was based on working stress method. But recently what we have resorted to is the limit state method. So permissible stresses are typically less than the yield stress of the bolt. So if you take a 4.6 grade bolt, it means the yield stress is about 400 kilonewtons and 400 megapascals. The yield stress of the material of the bolt is 400 megapascals. Sorry, ultimate stress is 400 megapascals and the yield stress is 60% of it, which is about 240 MPa. So this was the so this is a 4.6 grade board. But if you see the stresses, the permissible stresses are well below that. So uh, so the permissible stresses are well below the yield stress also. The yield stress is 240, but the uh, shear yield stress will be something like 240 by root 3, and it is even less than that. It is 100. So this is as per the working stress design, which is not currently in use. So, but let us design the same problem by limit state design. So ignore the options. If we have to design the same, if we have to solve the same problem by limit state method, first let us consider the limit state of shear failure. We saw that VDSB is equal to the number of shear planes into the net area or the shank area. So if the number of shear plates passing through the net area, the shank area of the NS into ASB plus NN into A and B. So this is the total area into FUB by root 3 gamma MW, gamma MB. This has to be less than or equal to the applied force. In this case, how many shear, what is the number of shear plates? So there are, if you consider this, this half is resisting the same. So you have 12 bolts. So you have 12, and it is a double cover lap joint. So there are two shear interfaces into two. Let us assume that then there is no shank and net separate values for a rivet. It's the same. So what is the area of this rivet? It is pi by 4 into 20 square. Into FUB. So forget about the permissible stresses. Let us take the ultimate bearing, ultimate tensile strength of the material to be 400. So in this case, it is 400 divided by root 3, and gamma MB is 1.25. So this is VDSB, and you can find out what this value is. It comes to around 1392 kilonewtons. And now you can also consider bearing failure. So in this case, the edge distance is not given. Just take it to be equal to the pitch itself. So just take E equal to P equal to 50 mm. What is D naught? D naught is the whole diameter. In this case, it is 20 mm. And the thickness. So thickness of the plate is 14 mm. And the thickness of the cover plates is 10 mm. So the bearing VDPB is given as 2.5 kb dt fu by gamma m. Gamma m. So 2.5 is this. What is kb? Kb is the minimum of so kb is the minimum of E by 3d naught, P by 3d naught minus 20.25. So E is equal to P. So the second one can be smaller, and that value is so this is about 0.58 in our case. So kb, and these two are, so if you take if the bolt is of grade 400 and the steel is of grade 250. So if you take the 250 if mild steel and the ultimate strength of mild steel is about 410 MPa, the bolt ultimate tensile strength is 400. So this comes out to be around 0.9. This is 1. So this least is this one, which is 0.58. So the least is 0.58. kb is 0.58. The nominal area, the nominal bearing area is this, which is d times 3. What is d? D is 20 mm. Thickness, if you consider the plate itself, it is 14 mm. That is obviously smaller because there are two cover plates resisting half of the load. So you can take 10 mm, but that value has to be multiplied by 2 because there are two such cover plates. So obviously 14 mm will govern the design. Into FU. So FU is either FU of the plate or the bolt. In this case, FU of the bolt is smaller, so you take 400 divided by gamma n, is 1.2. So this value is so this is about 1.3. Sorry, 2.5, 2.58 into 20 into 40. So this comes out to around 130 kilometers. Let me check. So this is the bearing capacity. This is the bearing force of one bolt, but there are 12 such bolts. So multiply by. So this is VDPB per bolt. So for 12 such bolts, it is that's about 1560 kilonewtons. So obviously, in this case, the shear strength will be the strength of the connection will be governed by shear. In this case. Yeah, so that value will be obviously higher than all the values here because it is based on the limit state design, whereas these are based on allowable stress design. So let us look at another problem. So weld we'll look at it later. We don't have time. We look at the simple problem. So this is a more recent one. So this is an out of plane bolted connection, out of plane eccentric bolted connection. The tension and shear force in each bolt of the joint is shown. So there is a connection that is given. This member, this member which is connected to this column is subjected to an axial force of PU, it's 250 kilonewtons. And you can see this line passes through the center of the bolt groove. So is there any moment that is transmitted onto the bolt? No. So this line passes through the center of the bolt groove. So this is the center of the bolt groove. This passes through the center of the bolt groove. So there is no moment. There is no moment that is coming onto the bolt group. There's only a tension and shear. And as usual, shear can be assumed to be taken equally by all the bolts. So there are 6 bolts here. And what is the shear force? So the angle is given. So this is the inclination is 3 in 5, 3 in 4. So this can be resolved in the horizontal and vertical direction. So this will be 0 points. The vertical component will be 0.6 times 250. And the horizontal component will be 0.4 times 250 kilograms. And these forces pass through the center of the bolt group. So there is no eccentricity. If it is passing through some other point, say if this line is tilted, if it is passing through this, then we need to consider this eccentricity E. And you also need to consider the moment, which is P times E. Pu times E. But that is not the case here. It passes through the center of the movement. You just have to find out the net tension is 100 kilonewtons. And the net shear coming onto the bolt group is 150 kilonewtons. So there are 6 bolts sharing the thing. Sorry, point. This is 0.8. This is not 0.4. This is 0.8. So this will be 200 kilonewtons. Yeah. This 4 by 5 is 0.8 and this is 0.6. So that's all it is. So the shear per bolt will be V by 6 and the tension per bolt will be T by 6. So 200 by 6 is 33.3. 150 by 6 is 25 kilograms. So this will be the right option. The welded connection, we'll take it up in the next class. That is also a simple problem. But again, this is as per the working stress method. We'll do a limit state solution in the next discussion. If you have any doubts, yeah, the problem, they are very simple. But even if you have any doubts with respect to these in-plane and out-of-plane connections, as I have told already, this resource is very helpful. This INSDAC teaching materials. So last time when I taught plastic analysis of structures, I referred to it. And this, if you go through chapters 30 to 34 in the website, it will be very helpful. It is whatever I spoke today is based on this material only. And you can also refer to the NPTEL lectures available in the portal. So I'll wait for some more time. If you have any doubts, you can ask. If you have any other doubts in some other topics also, you can ask. And you can also post it in that group which I have created, the Google group. I'll stay back for some time. If you have any doubts, you can ask. So they also have solved problems. Let me show it. You can look at this. We also have the solved problems in welded and bolted connections. That will be helpful for you for practice. Okay, I'll stay back for about 2 minutes. In case you have any doubts, you can ask. Stop recording. Thank you.